In this video, we're going to talk about intermolecular forces, specifically London dispersion forces. We're going to talk about the melting points that are affected by London dispersion forces and how they vary. And we're going to explain why that happens. Okay, let's get on with it. So, simple molecular lattices are molecules with a definite number of atoms and a definitive molecular formula. Now, in GCSE, you'll have been told that these are small molecules such as CO2, NH3 and H2O. And that's no different here. Okay, they have covalent bonds within them, so you can see hopefully two nonmetals, so therefore covalent bonds between them. Okay, but they have weak intermolecular forces between the molecules, and one of the intermolecular forces is London dispersion, which we're going to talk about today. So like I said, they're held together by strong covalent bonds. They've got weak intermolecular forces, and the one we're going to talk about is London dispersion. Now, they also have low melting points and boiling points due to the fact that they have weak intermolecular forces. Now, you're going to need to, over a series of 2 to 3 videos, see that those intermolecular forces split into 3 areas. One is London dispersion forces for this video. The second one is going to be permanent dipole-dipole, and the third one is going to be hydrogen bonding. Now, they also do not conduct electricity as there are no free electrons to move. Now, for electricity to carry current, or for a molecule, to carry current and therefore conduct electricity, you will need free electrons that can move, okay? And they can't move in simple molecular lattices, therefore they don't conduct. And before we go on to London dispersion forces, it's interesting to look at a solubility example. So solubility tends to depend on the molecule itself being the same as the solvent. So what do I mean by that? What I mean is a polar molecule will dissolve in a polar solvent, okay? Now, we're going to give you one of the most common examples of that. So if you look at this diagram right here, you can see that there's a kind of dark brown solution. You may have seen this in your lessons. This is iodine aqueous. So that's iodine dissolved in water. Now, water, and hopefully you're aware, is polar. Because water is polar, okay, the iodine is not polar because the iodine has the same electronegativity. So iodine and iodine, same electronegativity, I2. Whereas we've got water which has a difference in electronegativity between the O and the H. That means that the iodine won't dissolve very well because polar dissolves in polar. Well, iodine is not polar. Water is polar, okay? So therefore, there's not a lot of iodine dissolved in here, and hence, iodine is not its natural colour. Its natural colour is purple, so a solid iodine is a very, very dark purple. You can't see purple here, it's dark brown. That's because it is a non-polar dissolving in a polar solvent. Now, what's the opposite of that? Well, the opposite of that is a non-polar molecule dissolving in a non-polar solvent. So let's just take the iodine again. We know it's purple in normal life, okay? And if we put it into a non-polar solvent, well, the non-polar solvent we're going to choose is cyclohexane, and you can see this purple colour appears. So this purple colour is appearing because the iodine is dissolving much more readily in the cyclohexane than it would in the water above, and hence iodine in cyclohexane is a purple, a strong purple colour, which is a normal colour, okay? But if you dissolve iodine in water, it is dark brown because there isn't as much dissolving going on because the polarities don't match. So just to review that, polar will dissolve in polar solvents, so polar molecules dissolve in polar solvents, and non-polar molecules will dissolve in non-polar solvents. And there's your example of iodine here. Now let's talk about London dispersion forces, and the journey we have with London dispersion forces is first talking about something called an instantaneous dipole. Now, here is a normal atom, okay, and inside that atom, the electrons are moving all the time, so they're just moving and they could be anywhere at any time, okay, so they're just basically, there's lots of electrons and they might be over here, here, and they get distorted, and they get distorted because they're moving through space all the time. So what happens is the atom just changes ever so slightly. So the electron cloud moves towards this end. You can see towards this end it's delta minus, so a little minus. That means most of the electrons are around about this end, okay? Which means that a few electrons are here and the nucleus is here. So you get a delta positive this end and a delta negative that end, and that's called an instantaneous dipole. Now what happens next is that the electrons right themselves. They go in relatively the right point, and so the electrons are around the nucleus and everything cancels again. So this instantaneously happens, okay? Now this instantaneous dipole that happens in the atoms, in these simple molecules, okay, that will give an unequal distribution of charge, which is why you get the delta minus, you get the delta plus. But remember, it is tiny. It's a tiny, tiny force. It's a tiny bit of plus and tiny bit of minus, and then it disappears, okay? Now, what can happen is that if the instantaneous dipole in an atom, okay, is next to another atom, it can attract. So for example, the delta minus might attract the nucleus slightly closer towards itself because the nucleus is positive, okay? And then what you get is an induced dipole-dipole attraction. So this is an instantaneous dipole which has induced a dipole in the neighbouring atom. And there then will therefore be an attraction because it has pulled this nucleus slightly closer to here because negative attracts to positive. Okay, and we have that attraction. That's called a London dispersion force. Okay, so it's when an instantaneous dipole induces a dipole in another atom. And this happens in atoms, in simple molecules, all the time. So basically the electrons are moving all the time, so these things will disappear and appear, disappear all the time. And this is what attracts molecules to each other. Now, let's look at how this affects the boiling point. So first of all, the London dispersion forces are weak and present in all molecules. So we get the instantaneous dipoles and the induced dipoles in all molecules, okay? The strength is based, though, on the number of electrons, and that's really important. That's an exam answer. Number of electrons is where you need to look at, okay, to decide on what the strength is of these London dispersion forces. So if we look up here, we can see that we have a list of the noble gases, and you can see as the noble gases goes down, I'm going down, I can see 4, 27, 87, 166, 211. It basically means that we have got an increase in the boiling point. And the question is, well, why is this? Okay, and there's your increase clearly shown on a graph. Okay, so let's show this in pictorial form. If I have helium might have an instantaneous dipole like this. Neon is a bigger element. Because neon is a bigger element, it's got more electrons, higher number of electrons, so therefore the cloud is going to be more unequally distributed, and therefore these delta minuses and delta pluses are going to be a bit stronger, which means they'll induce a stronger London dispersion force, a stronger attraction between the molecules. And this carries on all the way through, so we've got a delta plus, delta minus, bigger amount of electrons, larger amounts of electrons. Because the electrons are increasing in number, the London dispersion force is getting stronger. We go to xenon, okay, that's again bigger. And lastly, we go to radon, again much bigger. So this increase in boiling point that we can see here is directly down to the London dispersion forces getting stronger because the number of electrons in each atom is increasing. Now this happens in multiple different areas, so you've really got to focus on the electrons. So when you're looking at something that's a simple molecule, look at its number of electrons. If it's a simple molecule and it has London dispersion forces, because you first have to identify whether it has London dispersion forces, okay, and we'll talk about that and the difference in intermolecular forces in the next video. But if you are sure it's London dispersion forces, you need to look at it and go, what's happening to the numbers of electrons? Well, if the numbers of electrons are going up, the London dispersion forces are getting stronger, and therefore my boiling point or my melting point is going up. And so that's what you see in group 0. You also see this in group number 7, okay? And those are the two most common examples. So let's talk about group 7 next. The same thing. But this time we have molecules, we don't have atoms. So we have F2, Cl2, Br2, and I2, and At2. You can see the number of electrons is going up massively as you go down the group. Electrons go up as you go down the group. we've got our graph again here. The graph is showing an increase. And then the question would be, in the exam, explain why the boiling points of group 7 elements increase as you go down the group. So our exam answer here is higher boiling points are caused by the increased strength of the London dispersion forces. So we have to refer, the really important thing is to the strength of the London dispersion forces. Then we have to explain why, because it says explain why in the question. So we have to say this is caused by an increased number of electrons down the group. Okay, so group 7, group 0 are the most common ones. Now, you don't often have to say this in an exam, but sometimes it's good, especially in the AS exam, if your school is one that does an AS exam, that you explain what the instantaneous dipole is and how it induces a dipole in another atom. Okay, and that is due to this unequal distribution of charge. Now, most of the time, though, the questions you ask only require you to put point 1 and point 2, relate the electrons to the increased strength of the London dispersion forces.